In just 72 hours, two stars exhibited such power that they became visible to the naked eye. A pair of earthquakes with a magnitude of 6 shook Venezuela, while a massive solar flare struck the only confirmed interstellar comet in our sky. Scientists called this period the 72-hour stack. But no one expected all these events to happen simultaneously, including the three-eyed comet, which was directly hit by a coronal mass. The probability of such a cosmic and seismic coincidence is less than 1 in 1,000. Is this a random coincidence or a sign that we are missing a deeper pattern? The accumulation of rare high-energy events over 3 days. If you're curious about how unlikely this is, let's figure it out. On average, there is possibly one nova visible to the naked eye each year, sometimes none at all. This time, two flared up within a day and a half of each other, both bright enough for amateur astronomers to notice without a telescope. In Venezuela, the region usually experiences earthquakes with a magnitude of 6 every 2 to 3 years. Two major earthquakes and a strong aftershock occurred in the same area in less than 6 hours. Meanwhile, the sun, already restless at the peak of its active cycle, ejected a coronal mass directly along the orbital path of an interstellar comet. This is so rare that it is only the third comet ever confirmed. If you add up all the numbers, the probability that all these events will occur within a single 72-hour window turns out to be less than 1,000, possibly even much lower, depending on the calculation methodology. Statisticians call this Poisson clustering. Sometimes chance deals the cards in a way that seems biased. The probability of seeing a pair of novae visible to the naked eye in 3 days is less than 0.02%. Two Venezuelan earthquakes of that magnitude in succession is about 1 in 10,000. Add to this the coronal mass passing by 3 eyes as it enters the inner solar system, and you will find yourself in a region where calculators practically refuse to work. This is why even experienced researchers call this event a stack. It's not just the rarity of each element, but how they intersect, making the entire period almost impossible. The phrase is already spreading in astronomical and geophysical circles as a brief designation for the week when the universe seemed to throw the rules out. The numbers don't lie. It's a higher-order statistical anomaly. That's why it's so hard to ignore and so tempting to investigate, minute by minute, to see how closely these events defying probabilities are actually connected. The clock starts ticking right after midnight in Universal Time. At 2:12 a.m. Universal Time on September 23rd, the first nova, V1935 Centauri, becomes visible. Survey telescopes in Chile and South Africa detect a flare within minutes. Automated alerts are recorded, and public confirmation arrives in less than an hour. In the local time of the Centaurus constellation, it is still deep night, but news is already spreading through international networks by morning in Europe. Closer to the evening of September 24th, 2021, Coordinated Universal Time, seismographs across the Caribbean region recorded a sharp surface rupture. An earthquake with a magnitude of 6.2 occurring near Meneg Grande in Venezuela. The epicenter was located at a depth of about 7.8 kilometers. The local clock showed 6:21 in the evening, just as the residents finished dinner. For several minutes, preliminary data began to flow into the information feeds of the Venezuelan Seismic Agency and were also recorded in global catalogs from the USA, GS, and EMSC. Less than 6 hours later, at 3 hours 51 minutes on September 25th, the Earth shook again. This time an earthquake of magnitude 6.3 occurred, a bit deeper, at 14 kilometers. This region shook once more. For the next hour, aftershocks occurred in the area, including one with a magnitude of about 5.8. Hospital records and WhatsApp messages documented the chaos in real time as medical staff rushed to help. Just 14 minutes after the second earthquake, at 4:05, another astronomical signal was activated. The star V7994 Sagittarius flared, reaching a maximum brightness of magnitude 6.2. Automated channels began disseminating information about the discovery in public feeds, while multi-wavelength sensors detected both gamma rays and X-ray signatures. Astronomy enthusiasts began exchanging notes with professionals, while in the background the sun approached a critical moment. On September 25th, a coronal mass ejection, launched the day before, swept through the inner solar system. Models predicted her arrival on the expected path of Comet 3/Atlas within 8 hours, with estimates centered around noon in Coordinated Universal Time. But the true match depended on the latest measurements of solar wind speed. Signals from space from the prediction center arrived for several minutes after each new reading, while scientists and comet watchers tracked the movement of the plasma front. Each time was recorded in Universal Time, but each event left its local mark. The telescopes in Chile operated in the pre-dawn coolness, Venezuelan hospitals suffered from evening power outages, and solar physicists observed real-time data streams. The stream of events, minute by minute, formed a timeline as rich as any recent one, each marker a point on the map of an unusual 32-hour window. A nova is not just a sudden glow. This is an eruption on a white dwarf, a dead star quietly siphoning hydrogen from its companion until the pressure triggers an uncontrollable thermonuclear reaction. For several hours, the light of the system can increase 100,000 times, overshadowing a billion suns. This is exactly what happened before dawn on September 23rd, when the star Vivo 1935 Centauri, a dim star in the constellation Centaurus, rose to a magnitude of 5.8. This is visible to the naked eye from a dark field, which is rare even for experienced astronomers. Gabriela Moyer, an astronomy enthusiast from Valparaiso, Chile, was the first to confirm the flash. She spent the night managing remote telescope sessions in search of something unusual. Despite the clouds and power outages, she persevered, driven by both excitement and the weight of leadership. Rumors of nova spread through Discord channels, but Moyer was waiting for certainty. When her report reached the Central Office of Astronomical Telegrams, the clock showed 12 minutes past midnight UTC. She had hardly slept for the last 2 days. Her signal triggered a wave of automatic confirmations across the southern hemisphere, and soon the coordinates of nova began to blink in global networks. The spectacle of nova lies in its physics. Hydrogen from the companion star accumulates on the surface of a white dwarf, compressing under gravity to temperatures exceeding 10 million degrees. Nuclear fusion ignites in a chain reaction, ejecting outer layers into space at thousands of kilometers per second. An explosion creates a shockwave that breaks through the expelled gas, heating it to the point of glowing visible light and emitting gamma and X-rays. In the case of V1935 Centauri, orbital detectors picked up a clear signal of gamma rays and hard X-rays when the optical brightness peaked. It was the imprint of powerful impacts, evidence that the explosion accelerated particles to speeds close to the speed of light and possibly formed dust in its aftermath. Less than 2 days later, another white dwarf in the constellation Sagittarius, V79994 Sagittarius, achieved a magnitude of 6.2, which was on the edge of visibility without the aid of a telescope. This discovery sparked debates as several research groups rushed to be the first to announce their findings, with their reports being shared between telescope logbooks and social media. High-energy satellites like Fermi and Swift detected the event almost instantly, capturing a sharp burst of gamma and hard X-rays. Internal debates at NASA and among the Fermi team delayed publication while the data was checked for false alarms. When the discoveries were finally announced, preprints flooded the scientific community, each exploring the physics of shocks and the particle accelerations behind the burst. The connecting link between these novas is the power of their shock signals, visible in light curves and high-energy emissions. This is not just an increase in brightness, but thermonuclear eruptions unfolding in binary systems, light years away from us, yet bright enough to leave their mark on our sky. The first earthquake occurred just after sunset near Manegra, with a magnitude of 6.2 at a depth of 7.8 kilometers. It was close enough to the surface for the fault to reach it immediately, shaking houses and causing power lines to sway. The local hospital, already facing a shortage of supplies, hurried to organize a triage of patients outside while aftershocks continued. Head nurse Marichela Rivas, just finishing her shift, found herself back in the thick of things, directing patients to colorful tarps spread out across the parking lot. Her voice, confident in the hospital's WhatsApp group, reported injuries and urgent needs while volunteers set up makeshift water supply points and moved the most critical patients from the cracked walls. 5 hours later, the ground shifted again, this time with a magnitude of 6.3, but at a depth of 14 kilometers, almost directly under the same region. The consequences of the earthquake developed according to the classic pattern of stress transfer. One segment of the fault shifted, loading the next. Seismologists from the University of Los Andes worked all night, mapping the progress of the rupture along the Ochre Fault. Their analysis indicated a typical decay of aftershocks, known as Maury's Law. Initially, the strongest tremors occurred, followed by a series of smaller underground shocks. An aftershock of magnitude 5.8 occurred, forcing patients and staff to evacuate the building again. The hospital cooks, engrossed in their work, became observers, watching the walls for new cracks and reporting when it was safe to return. The first hours after the incident were filled with improvisation. With 3 operating tables and intermittent power outages, Reverse and her team focused on the children and the most severe injuries. They brought patients outside during aftershocks, using flashlights to manage IV drips and monitor vital signs. Local radio stations broadcast updates from the hospital, relaying lists of needed supplies and safe routes for ambulances. During these hours, the hospital became a center not only for medical assistance, but also for information coordination and community interaction. Seismologists analyzing a cluster of events emphasize that, despite the time frames, the earthquakes followed well-known geological patterns. The Earth's crust in this part of Venezuela is constantly under stress due to the slow movement of the Caribbean and South American tectonic plates. When one segment shifts, the tension redistributes, sometimes causing a rupture nearby. Each aftershock reminded that in a week, when the universe seemed to be rewriting the rules, the ground beneath still followed its own laws. The peak of solar activity is not just a buzzword this year, but a daily reality. The number of sunspots has risen to 106, and the solar radio flux remains above 180. This is exactly the environment where coronal mass ejections become almost routine, with the sun ejecting dense clouds of plasma every few days. But now the situation is different, as something else coexists with these storms in the inner solar system. Object 3 and Atlas, the only third confirmed interstellar object, does not follow the usual scenario. Its orbit is highly retrograde, nearly touching the ecliptic, and it moves at a speed of over 60 kilometers per second, significantly faster than typical comets. This trajectory brings it within 0.19 astronomical units of Mars on October 3rd, a close flyby prompting Mars orbiter teams to be alert for potential opportunities for photography and spectroscopy. Most of the comets we study come from the Oort cloud, or the Kuiper belt. 3I/Atlas comes from a completely different star system, carrying materials and volatile substances that preceded our Sun. Its arrival in our solar system could not have been more fortuitous. Passing through the solar system at the peak of solar cycle 25, he encounters the most energetic and variable conditions of solar wind that we have observed for over 10 years. This makes the comet a natural plasma probe, an object whose coma and tail can show in real time how interstellar material reacts to intense solar activity. Dr. Stephen Burns, a geophysicist known for his research on solar-terrestrial interactions, called this event an experiment that occurs once in a generation. He notes that while we have observed the influence of coronal mass ejections on the comets of the solar system, we have never had the opportunity to see how this happens with an interstellar object. A close flyby near Mars adds an additional aspect as planetary scientists rush to coordinate observations with orbital spacecraft like TGO and MAVEN. Every piece of information gathered at this moment can help unravel both the origin of the comet and the physics of plasma interaction during the solar maximum. When the Comet 3 Atlas passes by Mars and heads towards perihelion on October 29th, it is not just a curious case, but a rare moving target for heliophysics and planetary science. Increased solar activity, the unique path of a comet, and the timing of this collision turn an ordinary solar storm into a scientific opportunity that will not occur again soon. October promises to be a month that will go down in history, with several moments when celestial observers and scientific communities can directly participate. The next important date is October 20th and 21st, when the Comet SWAN, designated as C2025R2, will approach Earth at a distance of only 0.26 astronomical units. It is about 39 million kilometers, and with the new moon and the peak of the Orionid meteor shower, conditions will be extremely favorable for observing the faint tail of the comet. For the best view, it's worth going outside after midnight, away from the city lights, and giving your eyes at least half an hour to adjust. Binoculars with magnification of 7 by 50 or 10 by 50 will be useful, and star maps or mobile apps will help locate the position of the comet as it glides across the sky before dawn. On October 29th, 3 Atlas spacecraft will reach perihelion, the closest point to the Sun in this passage, at a distance of about 1.36 astronomical units. Although it will not be visible on a bright sunny day, experienced observers may try to spot it at dusk or dawn, but only with great caution. Never look at the sun without certified solar filters, ISO 123.12.2, and do not use binoculars or telescopes unless the filter securely covers the front lens. Even a brief glance without a filter can cause permanent eye damage. For observing comets and hunting them, patience is the key to success. Dark adaptation is important, and red lanterns or dim screens will help protect night vision. The third important date is December 19th, when 3 Atlas will approach Earth to a distance of about 1.8 astronomical units. At this moment, the comet will be most accessible for amateur photography and visual observations, especially if its activity increases after perihelion. Platforms of public science, such as AAVSO, International Comet Quarterly, and the Comet Observation Database are already publishing calls for brightness assessments, sketches of tails, and time-lapse photographs. If you notice something unusual, such as a sudden bright glow, a change in the tail, or a suspicious shutdown, record the time, place, and equipment used, and then compare the records with others before publishing information on official channels. A responsible message helps separate real discoveries from noise and keeps data useful for researchers. For those organizing group sky observations, especially with children, it's important to discuss basic safety rules before darkness falls.